This is the video for section 3.1, extreme values of a function. And in this section, we are going to talk about the first derivative test and critical points. So let's make a few definitions to start with. Let's let f be a function. And what we're going to be interested in here in this section is in extreme values of a function. So in other words, maxes or minima of functions, maxima or minima. And we call that more generally, we call that extrema of functions. So we'll say that f of c is a local maximum if f of c is greater than or equal to f of x for all x near c. So if f of c is the biggest point sort of in a little local region, then we'll say f of c is a local max, as indicated in this picture. And correspondingly, we'll say f of c is a local minimum if f of c is less than or equal to f of x for x near c. So if we have sort of a little valley, we'd say the lowest point in that valley is a local minimum. And so as an example, here's a function f of x. Where do you think the local extrema are? Well, it has a local max at the point 2, 2. So it's not necessarily the biggest point on the whole graph potentially, because it looks like this function is meant to be increasing as x goes to negative infinity. But nearby to f of 2 is the biggest point around. So there's a local max there. And there's a local min at negative 1, negative 2. So let's make some observations about this picture. First, let's notice that at the point where we had the local maximum, f goes from increasing to decreasing as we move from left to right. So the slope of my tangent line goes from positive to negative as I move from left to right. And f goes from decreasing to increasing at my local minimum, at negative 1, negative 2. So the derivative goes from negative to positive at my local minimum. Let's also notice that f prime of 2, that appears to be a sharp corner, so f prime of 2 is a DNE, whereas f prime of negative 1, well, that looks like a horizontal tangent line, so the derivative there is equal to 0. So keep all of these things in mind as we go forward. This is going to help motivate our definitions. So we're interested in determining where a function has its local extrema, its local maxes and its local mins. And in order to find that, we're going to define a critical point. So we're going to say that x equals c is a critical point of the function f of x, if either f prime of c equals 0 or f prime of c does not exist. And it's a fact that critical points are the only points where local extrema can occur. And we saw in the last picture that indeed we had, we had a critical point of the type f prime does not exist at 2, and a critical point of the type f prime equals 0 at negative 1. So these are the only places, critical points are the only places where local extrema can occur. However, not all critical points are extrema. That is in red, that is bold typed. If I could do that on my, screen here. Not all critical points are extrema. Just because you find a critical point, it does not mean it's a max or a min. You have to do something more, and let's see an example of that. Let's consider the function x cubed. Now we know f prime is 3x squared, so if we try to find the critical points, we'll set this equal to 0 because, so it's equal to 0 if x equals 0. And notice f prime of x equals 3x squared. That's a perfectly continuous, nice function, so we're not ever going to have the case f prime DNE. So my only critical point is x equals 0. However, the graph of y equals x cubed, while there is a horizontal tangent line at the origin, the origin is neither a max nor a minimum. The function increases everywhere except at the origin. So here's an example of where we have a function with a critical point, but at the critical point no local extrema occurs. So in order to rule out bad things like this happening, we need the first derivative test. And the first derivative test says the following. If p is a critical point of a continuous function that is differentiable near c, but possibly not at c, so p is either a point such that f prime of p equals 0, or f prime of p does not exist, then f has a local max at p if and only if f prime goes from positive to negative. So we have a local max if and only if the function goes from increasing to decreasing at that point. And f has a local min at p if and only if f prime goes from negative to positive. So in other words, if and only if the function goes from decreasing to increasing. So let's see an example of how we can put all these definitions into practice. So I have a function f of x equals 1/3 x cubed minus x squared minus 3x plus 1, and I'd like you to find the critical points and then use the first derivative test to determine if these critical points are maxes, mins, or neither. So step 1, we need to find the critical points. So you should do this and then come back and watch the video. So to start, we take the derivative, x squared minus 2x minus 3, and we set it equal to 0. We notice that this is a continuous function, so there's no points where the derivative does not exist. We factor, we get x minus 3 times x plus 1, so my critical points are x equals 3 and x equals negative 1. Now, in order to determine whether these are maxes, mins, or neithers, we need to use the first derivative test. So what I like to do, the way I like to do this, is I like to put my critical points, and only my critical points, on a number line. And why do I do that? Well, what does it mean to be a critical point? It means those are the only points where the derivative can change sign. So if they're equal to 0, if that's where the function equals to 0, that's the only places that my function can go from positive to negative if it's a continuous function. So that's why I put them on a number line. And then if I want to determine the sign of the derivative, I can just pick a point in each of these regions, and that'll tell me what the sign of the derivative is in the whole region, because the derivative cannot change sign except for possibly at negative 1 and 3. So I'm just going to remind you what the derivative is. I factored it to be x minus 3 times x plus 1, and writing it in this form makes it really easy to check the sign. So I'm going to pick a point bigger than 3, like 4, and I'll say that f prime of 4, well, it's 4 minus 3 times 4 plus 1. I don't care exactly what it is. I just care whether it's positive or negative. It's positive, so I put a plus sign in that region on my number line. Then I pick a number between negative 1 and 3, like maybe 0. F prime of 0 is 0 minus 3 times 0 plus 1. Don't care what it is, just care that it's going to be a negative times a positive, so it's going to be a negative number. So I put a negative sign in the region between negative 1 and 3. And now I pick a number to the left of negative 1, like negative 2, and f prime of negative 2 is negative 2 minus 3, which is negative, times negative 2 plus 1, which is also negative. So a negative times a negative is a positive. I put a plus right there. Now, the first derivative test tells me that if my function goes from increasing to decreasing, in other words, if my derivative goes from positive to negative, well, you can just draw yourself a little picture, and you see that that should be a local max. And similarly, if we go from decreasing to increasing, or if the derivative goes from negative to positive, well, we should have a picture just like this, and that's a local min. And indeed, x equals negative 1 is a local max, and x equals 3 is a local min.